Ready? All right. Well, good morning to everyone here in Brno, and good early morning to people in the Western Hemisphere, and good evening to all those who are watching from the Far East. Welcome to the first block of tutorials here at InterSpeech. This one is on speech recognition with the next generation of Kaldi. I'm Sanjeev Khudanpur, and the other presenters with me today are Dan Povey and Piotr Żelasko. And
hey guys, I don't know if you can hear me from here.
Sorry?
Can you hear me? Just checking.
Yes, I can hear whoever you are, but you're a disembodied voice right now. But we can hear you.
Okay.
All right.
Oh, I hear. Okay, cool.
Oh, I see. Dan. Now I see you there. Okay. Hey. All right. So Dan's online. Okay. So let's get started. Do I push one of these buttons to get the slides on?
Okay. You guys don't need to see me yet.
Yeah. Okay. There we are. Right. So I just said what's on that slide. So let's move on. This is very briefly the plan for today. I will give a very brief selective history of how we got here. And then Dan will first spend mostly the first hour talking about finite state acceptors and differentiable Fsas. After that, we'll take a short coffee break. And after the coffee break, Piotr will come around and talk about how to do speech data representation, particularly with large data sets, data augmentation, all the kind of things you want to do with speech. And then we'll talk about how some special handling needs to be done when you're dealing with deep learning frameworks like Pytorch. And then we'll close out towards the end of the 3 hours with a 15-minute run through of an example. And after that, we'll hopefully spare a few minutes for Q&A. Right? So that's the plan. And you'll see the slide coming in again to show you where we are as we make progress through the tutorial. As far as I can tell, we can handle live Q&A a little bit because we've programmed each of our talks to be a few minutes shorter than what's out there. But if need be, we will defer questions to later. So that brings me to the next slide. So first of all, quick acknowledgements. So thanks to the InterSpeech organizers. Brno is a little bit special when it comes to this particular tutorial because Kaldi sort of started with Brno. Lukáš Burget and Petr Schwartz were in the original team at Johns Hopkins with Dan, who started building Kaldi. And later on, Karel Vasily. I don't know if Karel is here. Karel was a big part of it. So basically, like, Brno's fingerprints are all over Kaldi as well. But what you may not know is that after the workshop, 3 summers in a row, we got together in Brno for 2 or 3 weeks each to do little hackathons in this group to add features to Kaldi. So the connection is deeper than you might just think. So it's fitting that Kaldi version 2, we are giving a tutorial on it here in Brno again. Another special thanks to Yenda Trimal. Yenda sitting over there. Normally, Kaldi tutorials are done by Yenda, me, and Dan. But Yenda found himself in this position where he's the tutorials chair, and he said, guys, I can't be evaluating your proposal and be the tutorial giver as well. So he's not part of today's tutorial, but be sure the next version we do, he will have his old role back. And also today we have a few people online, a couple of, 3 of Dan's colleagues from Xiaomi, and a couple of, my colleague Paula and student Desh from Hopkins. They'll be answering, hopefully, questions on the chat or in the Q&A live because most of the people talking will be busy focusing on the slides. And of course, several students like Ashish and others who are using K2, Lhotse, their feedback has already helped make the toolkit better. Right? So moving right on to my selective history. This is my personal biased history. Don't ask me to be unbiased. But I'll start with the basics. So I was influenced by Jelinek and the IBM gang. So this is their view, or the old view, of doing speech recognition. You think about the speaker's mind producing a set of sentences, a sentence W, which goes through the vocal apparatus, produces a speech signal. It goes through some signal processing, produces an acoustic feature sequence. If you're thinking PyTorch A is a feature matrix, its rows are basically, let's say, feature dimensions. Its columns are time, so it's a stacked matrix. And then the linguistic decoder's job is to take this A and try to guess what W is. And so the standard formalism is W star is the argmax of the P of W given A, meaning find the W which maximizes the posterior probability given the acoustics A. With a little bit of rearrangement and using Bayes' rule, you can then decompose it and then drop one term to get the standard equation for speech recognition. Find, given an A, the W that maximizes the acoustic model probability P of W given A times the language model probability P of W. And where do we get this P of W given A given W and P of W from? Well, P of W, I'll keep it short for today. It's just think of it as a simple n-gram model. You can do more fancy things later on, like RNNs and so on. But just imagine that W is based on n-gram statistics. And what about P of A given W? Well, in the simplest case, if A is that little squiggly waveform up there, pointer, here we go. Yeah. If A is this waveform over here, and its transcript is cat and hat, then what you want is you want to model for the probability of this waveform given this word sequence. But of course, there are many, many possible word sequences. You're not going to have a separate model for each W, so you need some kind of parameterization. So the typical thing we do is each word has a pronunciation. In this case, we're using phonemes. And is pronounced a, n, and d, and cat is pronounced k, a, and t. The a in cat and the a in and are the same a, and the t in cat and hat are the same. And then for each phoneme, we then create a hidden Markov model. Here's a little example. And we can put these together to produce a model P of A given W for this acoustic signal A given this word sequence W, which kind of looks like this. So this is the composite HMM for cat and hat. What this means is all our model parameters are in these HMMs, like in the emission and transition probabilities of the HMMs. Once you have those, you have the model for P of A given W. So, and of course, I said that we have models for phonemes, but in reality, we create models for context-dependent phonemes because the a and cat might have different acoustics than a and man, because in cat, it is surrounded by two stop consonants, and man, it's surrounded by two nasals, and so on. So you can think of these as not phoneme HMMs, but let's say context-dependent HMMs, and their states, if you remember now, are called cenones. This is a term introduced by, I think, Meiyu Wang back in the 80s or 90s, and so on. Right, so this is standard speech recognition. Of course, the generative models, the HMMs over here, their emission probabilities used to be Gaussians or Gaussian mixtures. And in that setting, you have these standard estimation equations. So when the work started in the 80s and early 90s, people used to use maximum likelihood. So that's the first equation over here. You want to estimate the parameters theta. So these thetas are the parameters of the acoustic model, the Gaussian probabilities. You want to estimate them to maximize the likelihood of the acoustics A given the transcript W, for little n being the nth training sentence, and you sort of do this over all the training sentences. Already, by the way, in the mid-80s, IBM had formulated discriminative training. And then later on in the mid-90s, Cambridge and IBM had papers in MMI, maximum mutual information training, by producing lattices, because what you now want to do is you don't want to maximize the likelihood of the acoustics given words, but instead the maximize the likelihood of the words given the acoustics, the posterior probabilities, which ends up being a mutual information quantity. And then the work that Dan did in the early 2000s, 2002, 3, that sort of made this procedure pretty much the standard way to do things in speech recognition, where you have a generative model, but you estimate its parameters discriminatively. So, and by the way you think about it is these are what in these days you'd call a sequence level criterion rather than a frame level training criterion. But this existed in speech recognition long before neural nets. Another thing that happened that is quite important is around the late 1990s, early 2000s, the use of finite state transducers became quite important. The way this came about is that, well, first of all, you'll hear a lot more about finite state acceptors and finite state transducers when Dan gives the first half of his talk in the morning. And the AT&T guys sort of pushed this formalism. So very simply, although you'll see details later, a finite state acceptor is a finite state machine whose states can represent some abstract discrete history. So think of language model state. So if you're building a bigram language model, think about each state in the finite state acceptor as a word, which is the previous word. And the outgoing arcs from that state represents the probabilities of the words that follow. And you get this graph-like automaton with directed graphs. And that's your finite state acceptor encoding a language model. Finite state transducers are similar objects. They are basically pairs of labels instead of a single label on an arc. So for example, you could have a transducer which takes a sequence of words as inputs, and just like that example, cat and hat, produces a sequence of phonemes as outputs. So that would transduce a word sequence into a phoneme sequence. If there were a couple of different pronunciations for the word and, let's say you could say and with a D, and maybe you could delete the D optionally, then this is not simply one string going to another, but one string going to a graph and things like that. Or if you had a different phoneme model, for HMM rather, for the phoneme a in the context cat as opposed to the phoneme a in the context man, then you'd have different HMMs. So all these replacements or transductions are easily done using this finite state acceptor transducer theory. And that became quite popular. JHU actually had a role in that as well. It started becoming popular in one of our workshops, and Murat Sarashlar and Bill Byrne and we wrote some of the early scripting and code to use the AT&T open library, the open source library, the FSM library, to start doing speech recognition. Why do we do this? As Dan will tell you in a little more detail, these things end up making the decoding process very efficient. So you can use standard algorithms created for WFSTs to determinize, minimize, basically make the decoding graph compact and make the arcs non-redundant. For example, if you had many words beginning with the same phoneme prefix, you want to organize them in some kind of prefix tree so that you compute acoustics likelihoods only once for all the words that begin with the phoneme. All that happens automatically in these FSAs. So this was an important development. In the mid-2000s, I think IBM rewrote their decoder under Jeff Zweig to make it FSM-based. Stan Chen made a lot of important contributions to this. And I have a little thing over there which says, these are all very elegant. There's one part of FSTs which is not elegant, namely, when you want to replace phonemes with these context-dependent phones, if you use something like decision trees, that part is a bit ugly. So not everything is elegant with FSTs, but it's still pretty good. Going forward, in the early 2010s, we started replacing the Gaussian densities in the HML with neural nets. And of course, neural nets have been worked on for a long time. There are papers in the late 80s with Kevin Lang, Alex Weibel talking about neural nets and how to use them for acoustic modeling. In the 90s, there was a lot of work, including here in Brno, and Bourlard and Morgan and Hermansky are well known for their work with neural nets. A lot of this work involved thinking of neural nets basically as classifiers. Take a piece of acoustics, get a label for what phoneme or context-dependent phone or HMM state of a context-dependent phone is the target, and do classification. And then you get posteriors out of it. You get probability of a state given A at any time, AT. And then you convert it to a likelihood by scaling by some priors on the state and so on and so forth. And these became very popular for a while. And actually, the big breakthrough happened with this, not breakthrough, let's just call it a convincing moment, happened with Microsoft's paper in Interspeech, where they showed a 35% reduction in error rate on switchboard, which was a big system trained on like 1,000+ hours. And so everybody was persuaded. So again, neural nets have been around for a long time. A lot of people have worked on it. But the early 2010s is when something changed. It could be data. It could be computing. It could be optimization algorithm. I just say the planets lined up. In Indian astrology, these stars have to come into a certain configuration for good things to happen. And that happened. And now we all use neural nets for acoustic modeling, right? But another thing that happened sort of in the mid-2010s, if you will, is that the old way of doing neural nets, where you use frame-based training, where you need alignments for every frame to see what phoneme it is, that started going away. And these old ideas about maximum mutual information training and MBR, which are sequence-based, they got implemented in Kaldi and other places. So I've just referenced a couple of papers of some of us here in the tutorial, but there's a lot of work in this elsewhere as well, where you start using sequence-based criteria to do acoustic modeling, so MMI training. And by the way, we did use alignments in the beginning, but they're not critical. And later on, there are papers that show that you don't need the HMM-GMM system at all. You can do MMI training of the neural net straight from scratch. So this is where we were in the late 2010s, if you will. So what do we do next? What do we do to take it to the next level? Well, one thing that we found ourselves in, and probably a big part of the community, is that by now Pytorch and TensorFlow and all have become quite standard. A lot of software developers, a lot of students are very familiar with it. But when we started building Kaldi, especially the work at Brno, the original NNet work, these frameworks are not at all popular, even when we started building the NNet2 and NNet3. So we had a lot of proprietary, call it, well, not proprietary, it was open source, but handmade code to implement neural nets and so on and so forth. At some point, we decided we should move on because these other frameworks have a lot of support, and there are people behind it, and new things are being implemented, including optimization algorithms. So we convened a set of town halls, and many of you may have participated in it. These were in the fall last year. And we brought people together, and altogether there were 400 or 500 people who attended these. And we had a lot of discussion with academics, with people in industry, and people who develop frameworks. And we decided that it was time to go ahead and rebuild big parts of Kaldi to be compatible with these big frameworks. So with this context in mind, I'm going to sort of let Dan jump straight into what did we do about it. So the end of that town hall, we made a roadmap about how we were going to go about it. And a roadmap involved building 2 or 3 different projects. One of them is K2, which takes care of all the FSTs and how you can do automatic differentiation through them. The second one is called Lhotse. It takes care of all the speech data handling and I/O and so on. And the third part is called Icefall, and it's now also has a predecessor called Snowfall, where we try to put in the knowledge which is beyond the core libraries and tools about how to go about building speech recognition resources. So with this in mind, I'm going to hand off to Dan. Dan, when you're ready, please start and go. I think you can control the slides as well, right?
Can you hear me?
Yes, we can hear you, Dan.
And can you see me?
Yes, we can see you too.
Okay, so you just started becoming a little, your voice has started becoming a little bit unclear. If we have connection problems, I guess we may have to go to the pre-recorded version, but I'm hoping that won't happen. Let me try to go to the next slide. Cool. Okay, so in this part of the talk, this is like 25 minutes or so, I'm going to introduce finite state acceptors and WFSAs and WFSTs. I'm a little bit concerned that probably a majority of the audience knows most of this stuff. But the thing with these tutorials is we do try to cater to the lowest common denominator. But I'll try to make it somewhat interesting for those who've been around a bit. So let's start with finite state acceptors. So you've probably seen a diagram like this. It has states and labeled directed arcs. And there's one special state that's bold. That's state 0 here. That's the start state. And there's some states that are final that have a double circle. So this is a representation of a set of strings. And you can follow the path to see what strings are accepted from a start state to a final state. So here it accepts A, B, and B. So again, a representation of a set of strings. Now there's a notion of equivalence that comes with this, that 2 FSAs, okay, before we get to that, epsilon. So epsilon is a special symbol that means there's no symbol on this arc. So in terms of the string that's accepted by a path, you kind of ignore the epsilon. So this FSA still accepts A, B, and B. So this gives us a notion of equivalence, that 2 FSAs are equivalent if they accept the same set of strings, but of course not equal necessarily. Another important FSA definition is determinism. That an FSA is deterministic if no 2 arcs with the same label leave any given state. So the one on the bottom there is not deterministic because there's 2 arcs with A. Usually the definition of deterministic also includes that there are no epsilons. Although sometimes it makes sense to use a version of that that doesn't specify the epsilon thing, but most of the time, no epsilons. So FSAs seem to have been investigated by mathematicians long before they were really useful for anything. This is kind of in theoretical computer science that existed before there really were computers, or at least practical computers. So an acceptor is an automaton that only has one action to accept a string. As far as I can tell, one of the earliest practical applications of this stuff was in the Unix program grep. So in at least one version of grep, you turn the regex into a deterministic FSA that allows you to quickly test whether it's in a string. Also, the compiler tools Lex and Yak use this stuff. So I heard this anecdote from Ken Church that apparently there was a disagreement among the original Unix guys about how to implement grep. And one of them felt that they should use deterministic FSAs, and that's why there's 2 greps in Unix, grep and egrep, and one of them uses determinization. I think whether or not it's faster depends on the specific case. Anyway, the math for this was developed a long time before. So here's a mathematical definition of FSAs. I've tried to make this compatible with the way weighted FSAs are usually defined. This isn't the only way to do it. The kind of historical version of this that comes from automata theory doesn't have a set of transitions. It has a transition relation, but it's basically the same thing. There are a couple small issues with this definition that you might think, oh, this isn't quite the way I would have done it. One is that the transitions are, or the arcs, are a set. So you can't really speak of having repeated elements. Like a set doesn't support that. And there are certain algorithms that would naturally throw up repeated elements. Things like composition or replacing some label with another. You can get duplicates. And you just have to be a bit careful with published versions of algorithms because, you know, since duplicates are not possible in that formulation, nobody's going to bother handling it, right? So in OpenFST, it is possible to have duplicates. They're supposed to be forbidden, but it's not really enforced by the toolkit. So it can sometimes be a source of problems. Also, there's an asymmetry between the initial state, that there's just one, and final states. I believe the GTN guys, the Facebook's differentiable FSA toolkit, have actually taken away that asymmetry. They have multiple initial states, but we haven't done that. We actually go the other way, that we have a single superfinal state. I'll explain later. So here's kind of a list of the operations that you can do with finite state acceptors, or that are defined. Intersection is a one that's used a lot. Basically, when we intersect two FSAs, we find an FSA that accepts the union of, the intersection of those two sets of strings. You can read that list. You've probably heard of most of these. I'm just going to go through some of the more common algorithms to explain briefly what they are and how the algorithm is done. Actually, right now I'm a bit concerned. I don't want to bore people who have a lot of experience with this, so I'll go through this a little bit fast. So intersection, we want to find an FSA that accepts the intersection of the two strings. And it's basically a kind of pair construction, where in the output, each state corresponds to a pair of states in the input. So potentially, all pairs of states could exist, but in practice, not all pairs will be reachable, because basically there's only an arc between those output pairs. If there was an arc between both the input FSAs, basically with the same label on, and there wasn't always a matching arc. So the algorithm itself is pretty trivial. There's like a queue of pairs, and you process each one, and you find matching arcs. Determinization is another common one. Often, so determinization means finding an equivalent FSA that's deterministic. And often this is done in two stages. We first remove epsilons and then determinize. And the basic determinization algorithm involves sets of states. So each state in the output corresponds to a set of states in the input that basically is reachable from the start via the same string. And there's, instead of a queue of pairs, there's a queue of sets. And you start off with just the initial state of the input. And each time you find all successor sets. And then there has to be some kind of hash so that you can identify whether you already saw a particular set. It tends to use a lot of memory. Some implementations, as Stan Chen did this at IBM, actually save memory by assuming there will never be hash collisions. So it just stores the hash value. And if you have a good enough hash function, you can take that to be true. I mean, it makes a person nervous to rely on this, but it's what Git does. Like technically Git isn't guaranteed to always work because there can be hash collisions, but nobody ever has seen one. Okay, minimization. So minimization is generally done after determinization. And we're finding an FSA that's equivalent to the input FSA, but has a minimal number of states and arcs. Now, you might think that the way you would do this is just like start from the input and find identical states and then just merge those. But it turns out you can't really do that because there could be cycles of states that are identical, but until the next one in the cycle is merged, you can't tell that this one is merged. So so the basic algorithm is a partition refinement thing where you start with just two sets, final states and non-final states, and then you split the sets until you can't split anymore. I actually made a mistake in minimization. I contributed some code to OpenFST that extended our minimization to handle some new case. But a couple of years later, Mike Riley discovered that my algorithm was totally flawed. So that was a bit embarrassing. Yes. Okay, so weighted finite state acceptors. So with weighted FSAs, it's like an FSA, but we have costs on the arcs. So instead of a set of strings, this one is a weighted set of strings now. So this FSA will accept the strings, let's say B with weight 2.5, AA with, let's say cost, AA with cost 4.5, AB with cost 5.5. So we're summing them across along the paths. Now, obviously, this gives us a new definition of equivalence, that two FSAs are equivalent if they accept the same strings with the same costs. And there's costs on the arcs and on the final states. So what I just said is a little bit unclear in general, because what if there's two alternative paths from the start state to a final state that have the same string? In that case, what is the cost? So this is where semi-rings come in. I'll explain in a minute what they are more mathematically. But the basic idea is, how do we combine two costs of paths? And in the tropical semi-ring, we treat them as costs and we just take the min cost, as if we were solving some kind of map search problem, minimum distance. In the log semi-ring, we treat them like negative log probs, and we sum up the probabilities. So it's like negative log add. The reason for this tropical semi-ring was that apparently some Brazilian dude was like investigating that part of mathematics. And Brazil is like in the tropics. So more mathematically, a semi-ring is a set that has certain operations defined that satisfy certain axioms. This is one of these things that mathematicians love, like, you know, groups and sets and rings and stuff. It's a little bit like a field, like the real numbers, except we cut a couple things off. There's a few axioms that it doesn't satisfy. So some of them include that times distributes over plus. There should be a zero element and a unit element. We've got to be a bit careful though, because the zero element isn't like physically zero when we're using these costs. In the two common semi-rings that we use, the zero actually corresponds to plus infinity, and the unit corresponds to zero. So anyway, so what it comes down to is that when we combine alternative paths, in the tropical semi-ring we take the min, in the log semi-ring we do negative log add. So WFSA theory seems to have been developed by mathematicians for very abstract purposes, again, not really for any like practical purpose or applied purpose. It seems to have had an application in the study of infinite series, So suppose you have some kind of series expression that looks like a polynomial or a multinomial, and it has coefficients. So mathematicians wondered, for a given series, can it be expressed as a rational function, like some polynomial is divided by another polynomial? And it turns out that it can, if and only if it can be expressed as a WFSA. So, I mean, that's one of those things that probably you wouldn't really care about unless you're a mathematician studying that area, but that's what it is. So most of the algorithms, well, all the algorithms really that are defined for unweighted FSAs are also defined for weighted. In a couple of cases, it becomes a little bit more interesting. The intersection now becomes composition. That's just a new name. And although I think in K2 we sometimes call it intersection. So sorry about that. But now it involves multiplying the weights, or in reality, adding the costs. And there's also some new operations that didn't exist before, like weight pushing. Weight pushing is when you basically make each state sum to 1 if it were a probability. So it helps search to work better, but it's one of these things that preserves equivalence, so that the output of weight pushing is always going to be equivalent to the input. Like most unary algorithms have this property, that the output is always going to be equivalent to the input. So it's easily testable if you have a weighted test for equivalence, which they do exist. Determinization is another algorithm that's a little bit more complicated. So instead of sets in the determinization algorithm, we now have weighted sets. And these weighted sets are normalized with the smallest cost subtracted. So now the problem is that determinization might not terminate, because a given set of states can have an infinite series of different weights on it. It turns out that if an FSA lacks a property called the twins property, this is studied by Murphy and Mori, it's not determinizable, at least not determinizable by the standard algorithms. This next slide shows an example of an FSA that fails the twins property. The issue is that there's, in the top FSA, there's 2 self loops starting from those states 1 and 2 with a certain string on them, A here. And they're both reachable from the start state by the same string, in this case also A. So basically determinization will throw up different pairs of weighted sets. Now the tricky thing here is that in this particular example, we can find an equivalent FSA in the tropical semiring, which is the one below, that's deterministic. So in this case, it actually, for like a reasonable definition of determinizable, this is determinizable. But the point is it's not determinizable by the normal algorithm. So this is the weighted version of the math formulation that I mentioned previously. Now we're just adding weights to the arcs and to the final weight, to the final, we don't have a set of final states, we have kind of a function from the final states to the semiring. Okay. Sorry, I keep pressing forward arrow, but that doesn't do anything. So that's why I'm pausing each time. Okay, weighted FSTs. So a weighted FST is like a weighted FSA, but there's 2 labels on each arc. And they're conventionally called an input label and an output label, respectively. So we can think of a WFST as accepting pairs of strings with associated costs and weights. So this one accepts A, C with a weight of 2, C, D with a cost of 3, and so on. So notice that there isn't really a notion of correspondence between particular items of the string. Like it's not that the first A is associated with the first C or anything like that. It's just, they're just pairs of strings with weights. You can think of it as transducing input strings to output strings in some circumstances, but this can be a quite misleading way to view it. It's much better to think of it as a function from pairs of strings to weights. So one of the algorithms that becomes kind of non-trivial or interesting for weighted finite state transducers is composition. It's kind of the key algorithm. Now, composition is basically just like weighted intersection, except we do the intersection on the output labels of a first and the input labels of a second. So here the Greek symbols beta, those are the symbols that we match. And the other labels, the inputs of the left side and the outputs of the right side, they don't participate in a very interesting way in the composition. They just kind of, they go along for the ride, so that after you match the inner labels, you keep the output labels. So in this case, we only end up with the A and C, but it's the B's that we sum over. It's a bit like matrix multiplication, and that there's like this inner symbol, K here, that we do a summation over. Of course, this is summation in the semi-ring. It's possible to do determinization on WFSTs. It's just done by converting them to WFSAs, though. The standard thing is we make the output label part of the weight. There's a thing called a Gallic semi-ring, which is just called that because some French mathematicians, I think this must be Riley's idea or something like that. So because some French mathematicians were using this formulation. Yeah. And with minimization, the same. We turn it into an acceptor. In fact, we turn it into an unweighted acceptor by turning the weights into like discrete things. You have to do this after pushing, because if you don't push the weights to kind of normalize them, there can be things that are equivalent, but you wouldn't notice it. Well, another way to minimize is to reverse, then determinize, then reverse, then determinize. It has the same effect. So the most useful application, or the first big useful application of WFSTs, seems to have been as a tool for ASR decoding. And the standard thing, most of you, I'm afraid, in the audience will be very familiar with this, is Hclg decoding. This is the AT&T guys came up with this formulation. Most of them are at Google now, but they were at AT&T. So the standard formulation is H is the HMM topology. Let me go through the next slides. I describe each one in detail. So H corresponds to the, damn it, the slide is actually wrong. It's not triphone context. H is for the HMM topology. So in this case, the three-state left to right HMM. So on one side, the label is the context-dependent triphone. In this case, A/A/A. And on the other, it's kind of numbers that describe the C-nodes, the clustered HMM states. Of course, this is in the triphone case. And these days, it's becoming more common to have context-independent phones and to have a much simpler topology called the CTC topology, where we have this shared blank, and then each state just has its own symbol that can be repeated once or more, but then you can have blanks. And this is done in conjunction with subsampling, so that instead of 100 frames per second, we start with an input of 100 frames per second, and then we subsample to like 4 times less or something, so that you can have a one-state topology, and you still won't be able to consume phones too fast. And there's, yeah. So the C part is the context dependency transducer. This is kind of nasty, and it's becoming less and less necessary because fewer people are using context-dependent phones. So I think we don't really need to talk about this, even for young people. Hopefully they just don't need to know it. L is the lexicon. Here's an example with cat and dog. So one side is the phones, the other side is the words. And G is the grammar. This is a tiny example, but in reality, this will actually be huge with millions of states if we derive it from an n-gram language model. Like most applications, it's better to use an n-gram language model than just a tiny grammar. Okay, so what Hclg means is that we compose Hc and L and G. In reality, if we just compose them, it wouldn't be that efficient to decode with. We have to do some other stuff. We have to determinize and minimize. And then if we want to determinize, there's some complications, because if our lexicon has homophones, which means two words with the same pronunciation, the L will be determinizable. So, so we have to make them all distinct by adding these fake phones called disambiguation symbols at the end of the pronunciations. And then we have to take steps to deal with those later by removing them eventually, or by copying them around. So anyway, this is all described by the AT&T guys or by Maury, like in his Springer Handbook chapter on WFSTs. So it's possible to view ASR decoding as a composition between two FSAs. So one FSA would be this Hclg, which I'm not drawing because it's very big. And the other thing is basically the neural network outputs. And if they're a matrix, we view it as an FSA with a regular structure. That might look something like this picture. So in principle, you could convert that into an actual FSA and just compose with Hclg and then find the best path. Of course, that's totally impractical because the number of states would be the number of states in Hclg times the number of phones, right? And the size of Hclg is usually like a few gig at least. So this would, you know, blow out your memory. So in practice, you have a different algorithm with pruning and stuff that's more kind of hand-coded. But this is a good conceptual way to look at it. So this is just about the end of this talk. I think we're a little bit short. You guys can have a longer than normal break. I hope they have like good coffee over there. Do they? Let me know if they have coffee in the break. I don't like it when conferences are stingy about that stuff. I'm sure the Brno guys did a good job.
Right. Hey, thanks, Dan. That was a nice, quick introduction. So just to recap, we have FSAs, think of them as collection of strings, WFSAs, weighted collections, WFSTs, same thing but on pairs. You learned a little bit about the log semiring and the tropical semiring. Think Brazilian when you think tropical semiring. And also decoding Hclg. So these were components which you'll need because once Dan starts talking about K2, he'll refer to how some of these operations need to be taken advantage of, or the algorithms for them to do the autograd for WFSTs. So what we have scheduled is actually a 5-minute break just to stretch your legs if somebody needs to run to the bathroom. What we'll do is we'll take questions in the meantime here. So those who are staying in the room and those online, if you have any basic questions about FSAs, ask them now. Otherwise, we'll just let everybody stretch for a few minutes and start in 5 minutes.
We could probably take it cool for now because I think the real questions, if any, will come at the K2 and Lhotse sections, right? That's the new stuff.
Sounds good. So let's take a 5-minute break. And if you haven't seen somebody for 1.5 years and you see them now, you can say hello to them.
Yeah, unfortunately, I can't see you guys. The video doesn't show me the audience. I'm sure that's for good reason.
Can the remote participants see the video Okay, Dan, see if you can play around because you should be able to see my face. I mean, you won't see the rest of the room.
I can't see your face. I don't know. It's not
Okay.
showing me.
I mean,
your
my face is not worth looking at, but you know.
It just shows me the presentation. That's all I see.
Okay, all right.
And my face.
Great, yeah.
Can you see my face?
Yes, we can see you, Dan. In fact, right now
Okay.
they've set it up so that both you and I are visible in two different
Okay, cool.
boxes. Right.
Okay. Well, let's not worry about this. I'm
Okay.
sure whatever
All right,
it is,
let's
it
not
can't
worry
be
about it,
changed.
yeah.
So, see you guys in 5 minutes.
Yep.
Bye.
All right. Dan, can you hear me?
Refreshments like over there, what have they got?
Yeah, okay. So people are trickling back in. Give them another 30 seconds and then we can start.
So what are the refreshments like?
Let me see. I'll tee up the next slide. Okay. All right, everyone, please settle down. We will start the next section of the tutorial.
Okay, guys.
All right, Dan, go ahead.
I'm actually curious. What are the refreshments over there? Is it good? Or it's just coffee? Okay, maybe your audio isn't showing up. I can't hear. So, okay, we better get down to business. Okay. I'm trying to go next slide and nothing is happening.
Dan, are you able to control it or not? Ah, you are. Okay.
Okay, now it's working. Okay. So, now it never rains, but it pours. So did you answer the question about the refreshments? I'm just curious.
And I couldn't hear you.
Oh, okay. Can you hear me now?
Yeah, I can hear you. Sorry, I should say I couldn't understand you.
Oh. Is the audio quality okay?
Yep, all good.
Okay, sorry. Okay, so I guess we better get down to it. So in this presentation, I'm going to introduce K2 and explain the kinds of things you can do with it. So this is just a super quick run through. So we do this brief run through and then I describe the basic principles of how it's implemented and what it can do. Okay. Sorry, there's a lot of latency on the next slide button. Okay, introduction. Okay, so K2 is a Python package that adds differentiable finite state acceptors to Pytorch. And we may eventually support other toolkits. For now, it's just Pytorch. So here's an example. If you import K2, you can create an FSA from a string and display it like that. One thing that you'll notice is might be unusual is these final probabilities are dealt with in a different way from OpenFST. We have this special final label, -1, that goes to a super final state. Yeah, I'll get to that a bit later. So the reason we call this an acceptor toolkit instead of a transducer toolkit is that it's simply that transducers aren't really first-class objects. We have this general notion of attributes that we can add like extra labels or extra costs to an FSA, and we just treat transducers as a special case of that. So remember when I described the intersection algorithm. Guys, people are telling me that the audio quality is not good. Okay, apparently not. Can you guys hear me okay from Brno?
No, we're hearing you quite clearly, no problem.
Okay, that's good, that's good. Yeah, so the intersection algorithm, it doesn't really involve all of the labels in a very non-trivial way. If you just treat it as an acceptor with the output labels of the input one and the input labels of the right-hand one, that's basically how the algorithm works. And you can do everything you want to do by attaching extra labels to things. And I'll explain how later. So this is an example of, we can also read the OpenFST format. It converts the OpenFST style thing into our format where we have a special super final state, and then the final probs are represented as arcs with label -1. So it's also negating the cost, because in K2, instead of storing things as costs, we negate and we store everything as scores, which is just the opposite, the negation of a cost. So all of those positive costs in OpenFST become negative scores in K2. So the basic purpose of K2 is so that you can implement all kinds of ASR algorithms easily in Pytorch. Things like CTC training, lattice-free MMI training, fast GPU decoding. It's not really specific to I don't like the word end-to-end because I think it's meaningless, but it's not specific to so-called traditional non-end-to-end ASR. It can be used in all kinds of so-called end-to-end stuff. And it was designed from the bottom up with GPU acceleration in mind. So all the data structures are geared towards efficiency on GPU. So most of the time, K2 operates on batches of FSAs. So you don't work on just one FSA at a time. You work on a whole mini batch. This example shows aggregating multiple FSAs into one object. And they're all stored in like a single array, basically. I'll explain how soon. So this little snippet of code shows how you create graphs for CTC alignment in K2. I don't want to go into too much detail here. The point is that it's just a few lines of code, and it creates these things as generic FSAs. So, of course, it's very possible to just hand code CTC, right? That's what Pytorch's CTC or Warp CTC does. But it's much nicer if you can do it as a more generic algorithm, because then it's flexible, right? You can change the topology. You don't have to do CUDA coding to do that. So next thing you would do to do CDC is take your neural network output and turn it into something called a dense FSA vec. And that's that FSA with a regular structure, like I showed you at the end of the last talk, that represents the neural network outputs. It does a little bit of manipulation or copying of the output tensor, and it relates to the special symbol -1 that we use for the final prob. The basic idea is that we don't allow -1 except on the last frame. And on the last frame, we don't allow any other symbol apart from -1. It may seem a little bit ugly from a user point of view, all of this business with the special symbol for final probs, but it's a very huge simplification of the internal code. Because if you've ever coded any FST algorithms, you'll know that final probs behave very much like arcs. Like if you're coding an algorithm, and if anytime you do something to an arc, you've normally got to do the same thing to final probs. So it simplifies things greatly if you can just treat it as a normal arc. So the next stage, if you're doing CTC, is to intersect that dense FSA with the CTC graphs. And this intersection has pruning, so we display it with pruning just so you can see what the lattice looks like. Then we get the total scores of the lattices, and that gives us an array of numbers that's like the CTC scores or the negative of the CDC scores from each of the graphs. And this thing is differentiable. You see the grad FN there. That shows that Torch is like ready to differentiate this thing. Of course, if we were to have set requires grad equals false, it wouldn't have given us that. So this framework makes it very easy to implement things like CTC, MMI, MPE, and BR using like standard tools. So if you want to decode, you can use the shortest path, right? Shortest path algorithm. So you can do that during training too to get alignment. So this shows us getting CTC alignments. And there's like two versions of the alignments. One is the frame by frame alignments from the neural net. And the other shows us with just like one copy of each phone, because the CTC topology allows repeats as long as there's no epsilons in between. So we can use some special K2 invocations to recover the original symbol sequence from this lattice. It just shows you some of the flexibility of the toolkit. So to understand what's really going on, we've got to understand ragged tensors. So this is the the fundamental design principle of K2, I guess. I actually spent a long time thinking about this design. And for like a month or so, I was just thinking and thinking. Eventually came up with this. It turns out that it's the same as what TensorFlow uses. They have the exact same data structure, but I wasn't aware of this at the time. So a ragged tensor is a representation of a nested set of lists. So like vector, a vector event in C++, but it could be arbitrary levels. But it's a fixed level. It's not like a Python nested list that could have the numbers at any level. So here's an example. If you want to represent this nested set of lists, we represent it as three sets of as three linear arrays: the values, the row IDs, and the row splits. So the row IDs tell you for each value what row it's in, and the row splits tells you where each row starts and ends. And we can also extend this to higher levels, more levels of nesting. So this is one that has the 3 axes instead of 2. So you would index it with 3 indexes if it were a hierarchical list. But you can also access it linearly using these row IDs and row splits. There's 2 levels now of the row IDs and row splits. Row IDs 2 is like the bottom level of the values, and row IDs 1 maps from the intermediate list to the top level lists, or to the top level index. So once you get used to this, it becomes quite intuitive to deal with. It may seem a little bit strange at first, but you can do a lot of things efficiently on the GPU if you use these data structures. So this is what it looks like to access a ragged tensor from Python. So it has a number of axes. In this case, it's 2. This is kind of like the endin of Torch. We're going to try to unify things a bit better in future. And it has the shape information as these row splits and row IDs. We can print these things out, and they're basically torch tensors. Internally, they're backed by a torch storage. That's how we can make them look like a torch tensor without copying. Now you can actually reconstruct the row IDs from the row splits. So they contain the same information, but the row splits has a little bit more because there might be empty lists. Wait a minute, I'm trying to go to the next slide. Nothing's happening. Sorry, guys. Okay, so why ragged tensors? So ragged tensors aren't just a data structure for storing things. They're also a way that we can implement complex algorithms on GPU. So in GPU programming, it's all about launching arrays of threads, right? We launch arrays of threads that are going to run the same code, but they all get kind of a different set of indexes. But these are linear or rectangular arrays. And it's very inconvenient to work with irregular length things because you're going to have to either loop or kind of waste elements in the rectangular list, depending whether you like pad or whatever. And basically, it can become very, very inefficient if you have data that has a nasty structure. Let's say that has one long list and many small lists. And that kind of thing can happen. So what ragged tensors do is they let you launch a single linear array of threads and have it process this arbitrarily structured data in an efficient way. Basically, we have to look up the hierarchical indexes from the linear index into the values. We can look that up using the row splits and row IDs. I'd like to draw your attention to one aspect of the code here, that we have a special convention for the indexes. So let's suppose we have a tensor with two axes, a ragged tensor. Think about an index into the values. That index conceptually represents two indexes, right? Because it represents both the the hierarchical index into the array. So we call this an index 0, 1 because it contains the information for levels both 0 and 1. So basically, we have a special naming convention that describes like which indexes any given index represents. In this particular case, it's not really that hard if there's just two axes, but it gets a lot more complicated when there's like 3 or 4 axes. So having a special convention to know what an index represents helps us to write bug-free code. Okay, 1 second. Trying to do next slide. Maybe it didn't work. Let me try again. Okay. So in K2 and FSA, at the C++ level at least, it's just a ragged tensor of arcs. So an arc is like a struct with 4 members: a source state, a dest state, a label, and a weight. And we can specify in FSA as a list of arcs plus the number of states. We just specified the final state, which is the last state, basically. And our convention is that state 0 is always the start state, and the final state is always the last numbered state is always the final state. So given that, we don't really need any side information. If we just have that array of arcs, where the first index is the state number of the source state, then we have all the information we need to represent an FSA. So that's it. We just construct a ragged tensor of arcs, and that represents an FSA. The final state always has no arcs leaving it, because it doesn't make like it's a super final state. If you remember that concept from OpenFST, it's like states that's more final than the final states, and nothing can ever leave it. So yeah, in C++, an FSA is just a ragged tensor of arc. In Python, we actually add some more logic that handles things like so-called attributes and handles autograd and things like that. So there is a bunch of extra logic. We're going to move that to C++ in future. So there's actually 2 cases of an FSA. One is a ragged tensor with two axes. That's just a single FSA. And the other ragged tensor with 3 axes, which is like a list of FSAs. And almost always in code, we use lists, meaning almost all the internal code will operate on a 3-axis FSA, and will like promote things if necessary temporarily. The idea is that in GPU programming, you want to avoid loops at all costs. You always want to do everything in parallel. So I want to go through some of the key features of K2. First thing is just to list the kinds of algorithms that we support. We support composition of FSAs or FSCs, finding the total cost or the log prop. This is what we did in the CTC thing, right? We get the total cost of the lattice in the log semi-ring, and that gives us the CTC score. Determinization and shortest path. Shortest path is like in decoding, get the best path. There's also a lot of kind of auxiliary algorithms that are needed for this and that, or that are needed as part of the main algorithms. Let's try to go to the next slide. Yeah. Oh, sorry. This is still the main algorithms. I'm trying to describe on this slide the purposes of the different ones. So composition is used in almost everything. And there's finite state acceptor composition and transducer, which is just done by acceptor composition, but we do some label swapping. There's a determinization. Right now, we don't have a GPU version of that. Eventually we will, but it's usually not necessary on GPU. And so on and so forth. There's a lot of little algorithms, things like clean closure or inverting, which means swapping input and output labels. The output labels, we store them on a special attribute called aux labels. So the regular labels of the FSA are the input labels, and the output labels are the aux labels. So we swap those two things when we invert. Yeah, you can see this list yourself. The left-hand side is what the algorithm is. The right-hand side is what kinds of things we use it for. So the way AutoGrad is done in K2 is for each operation, we keep track of which arcs in the input FSAs each output arc corresponds to. Now you need to know that these algorithms are not in place. They're kind of out of place, like there's an input and an output. So basically we construct a map from the output arc, the index of the output arc, to the corresponding index of the input arc. So let's think about the algorithm. Let's think of it composition. In composition, there's two input FSAs, and each output arc will correspond to like one input arc in each of them. So there's two arrays that tell you the input arcs for each output arc. And that's just a linear array because there's only one. But in some algorithms, each output arc could really be a chain of input arcs, like in epsilon removal. So in that case, the arc map is a ragged tensor. So the algorithms in C++ will output these things, these arc maps. And the Python code uses the arc maps to implement fast AutoGrad. So when we backprop things, we basically copy the gradients back to the original input arcs. So the idea is that the output arc's score is the sum of the scores of all of the corresponding input arcs. Now that is naturally the case in most of the algorithms. The only one that it isn't quite the case in is determinization, but we can change the algorithm slightly so that it is true. So at the Python level, we use torch.autograd.function to do this backprop. It's not too hard. At some point, we're thinking about moving all of this logic to C++. It turns out that the way Torch works in C++ is quite similar to Python. Like the interfaces are currently quite similar. So it's not super hard. So one of the things that I'm proudest, before we get to that, I want to talk about the meaning of AutoGrad for FSAs. We're not getting too deep here. We're not asking like about what it means to differentiate with respect to an FSA. It's just a mechanical thing, the same way it would be for any like torch operation. Of saying we have some loss function, say, and we want to backprop the derivatives of that back to the inputs. And as long as it's like an appropriate, like continuous function of the input, there's no problem, right? So in most of these algorithms, in all of these algorithms, each output arc score is just the sum of the input arc scores. It's the scores that we're differentiating, not like the structure of the FSA. So we kind of treat the structure as constant and ask about the derivatives of the scores. And the AutoGrad doesn't go deeply into the C++. It's just done by these arc maps. So it's not like we have individual tensors that we're manipulating and they each store some kind of back pointer or whatever. The AutoGrad is done kind of using knowledge of the algorithms and using these arc maps. So yeah, what I was saying, one of the things I'm most pleased with in K2 is the concept of attributes. So the idea is we attach named attributes to the FSAs, and they're quantities that are indexed by arc index, meaning they're arrays that have the same length as the number of arcs. So you can set an arbitrary attribute name like LM scores. It's not a special name. It's just an arbitrary string. That in this case, we're attaching a random vector as the LM scores. And then we do some kind of algorithm. And in the output, we still have LM scores. They've been propagated automatically. And the same thing happens for integer scores. Like here, the extra labels is also some integers, right, that we've attached. And those also have been propagated to the output. And all algorithms will propagate these things. Now, some algorithms will turn linear attributes into ragged attributes. So here we added the extra labels as like a random array of integers. And we did remove epsilon. And now look, it's a ragged array. You see there's sublists. The reason this happens is that remove epsilons will in general turn chains of arcs into a single arc, right? So if those arcs had labels on them, now we have a bunch of labels for a given arc. Now in this particular case, there was no epsilons to remove, so each list has one sublist in. So it's actually desirable in some cases to turn these ragged attributes into linear attributes. So there's a function called expand ragged attributes that will do this. The reason it's called expand is that in general it might have to alter the FSA structure by turning arcs into chains of arcs. So this would effectively be undoing the remove epsilon if the remove epsilon had done something non-trivial here. So as I said, currently we only support Pytorch. It's going to be a lot of work to support other toolkits, and we may do it eventually. The issue is that not all toolkits work quite the same. Like they have different, like some of these deep learning toolkits are all about like multi-device stuff, and they just don't all have a one-to-one mapping basically. But in any case, it should be possible to do for other toolkits because we're trying to keep the internal code fairly independent of Pytorch. It's all done via wrapping, so that even though we're using torch storage, it uses K2's own like wrapper thing. Maybe you don't really need to know this. So like I say, the core code is all C++. The front end is in Python. The backprop and the attribute stuff is all in Python. We're actually considering whether to move this code all to C++. It's going to be a bit harder to maintain because not so many people know C++, and there's all that PyBind 11 stuff, right, to make it visible in Python. But the advantage of having this in C++ would be that we could more easily deploy systems in C++ binaries. Like a lot of the times when people want to deploy systems, they don't like to use Python for their production. And that's why people use Torch script to export things to C++ program. So we'll see. We haven't 100% figured this out yet, but we'll probably move more things to C++. So I think we might actually be okay on time. I'm talking about this presentation here. Okay, so K2 future plans. Mostly we're working on Icefall right now. We're going to talk about Icefall later. We're continuing to refine and refactor K2. There's a few algorithms that we haven't yet implemented and need to implement things like determinization on GPU, but there's nothing that's really blocking for us right now. We have most of the things we need, so we're mostly working on the recipe layer right now. And you can already use K2 as a fast Pytorch compatible decoder. I'm not saying it's necessarily better than Kaldi's GPU decoder, which were done by NVIDIA, but it's fast and it's easy to understand, at least a lot easier than that, than Kaldi's one. So, summary slide. Sanjeev, maybe you want to go over the summary slide this time. I think having the variation of voices is
okay, Dan,
a good
thanks.
thing.
Yeah, yeah. So yes, we're doing well on time, Dan. In fact, you're right on the dot. So again, like, to very quickly recap, the main mechanism for implementing FSAs in K2 are these ragged tensors. So it's just basically a bag of arcs, and since you batch them up, you have the ragged tensors needed for that. The thing that I found very interesting about the way Dan did this is this idea of attributes. That way you can not only keep things like a transducer's output label in the attribute, you can keep language model scores separately, you can do a whole bunch of things. And then it also helps with some of the determinization algorithms by using this Gallic semi-ring idea. And then the other thing, of course, is that to do AutoGrad, one thing to think about is that you could always go down to the code level and do the standard AutoGrad by doing the the data dependency graph the way a compiler does it. But since we know how composition algorithms work and so on and so forth, you can take advantage of that and keep track for every arc of what are the other arcs through which its costs are computed. And that way you can backprop through it by knowledge of the composition and the minimization algorithms and so on. So that's what makes this special rather than general purpose AutoGrad that you'd have. So again, remember the key things are that FSAs are implemented as ragged tensors, and then you do them in batches, they're GPU optimized, and so on and so forth. Dan, we do have time for a few questions. By the way, there have been a few questions in the online Q&A, and Piotr and I have been answering them.
Cool.
Yeah,
I'm afraid I can't see the Q&A, so people will have to tell me if there's any.
Yeah, so far it looks like we've answered the questions, Dan. There was one interesting one about, Piotr, do you want to repeat the one about the ragged tensors? And yeah. Or maybe I can. Yeah, so, yeah, Dan, the question was, does a ragged tensor contain mixed types in an array? There was a slide with example of having state numbers and weights in the same ragged tensor.
Yeah, no, it's not mixed type. It's like in C++, like, a vector event or something. It's a fixed type, just like a torch tensor would be. Now, you can store a struct, though. You can template it on a struct, like we do for FSA. So in that case, it's mixed in a sense, but it's kind of structured, you know what I mean? Oh, it turns out that I just have to scroll down. That's where the, oh, wait a minute.
Yeah.
Okay. The issue is that my window is too small.
Yeah. By the way, Function did answer that question at some length.
Okay, cool.
Yeah.
Cool.
Yeah. And then the last question that just popped up was, it's a more philosophical type of question. What are the advantages of using K2 compared to regular Pytorch? I may have indirectly answered it by saying that you can do AutoGrad directly as well. It's just going down to the machine, program level, whereas here it's done at the algorithmic level. Dan, do you want to put it a different way or a different answer?
Well, I mean, I guess it's about speed and flexibility. Like, of course, any program that you can implement in C++, you can also implement in Python, right? It's just going to be like 1,000 times slower. So like K2 implements a lot of things that you couldn't, with any reasonable efficiency, implement in C++.
Okay.
Sorry, in Python.
Yep. So I think it was Peter Shijin. Hopefully we answered his question from Yandex, I think. Yeah. Other questions from the audience here or others online? By the way, others online, there is a way that you can raise your hand and we can enable you to ask questions by voice. So those who are online, you can use the option if you like. So does anyone online want to ask a question verbally? Oh, Thomas has a question in the audience. Go ahead.
Yeah, the question. Maybe you can repeat it.
I'll repeat it for Dan, yeah. Or
are there any technical constraints on the length of the audio that you can process with K2?
So Dan and others, the question is, are there any technical constraints on the length of the audio we can process with K2?
I mean, so K2 would be worried about the size of the FSAs rather than the size of the audio. So at some point, you're going to bump into GPU memory limits. And also, we do actually make all the integer types be int32. So the maximum number of states that you can have will probably be like 2 million approximately. Now, but it doesn't really interact with audio links because like we use print composition, right? So the number of states in the lattice, this is probably the large enough to keep it, the length was long. Of course, there's going to be numerical roundoff problems. There's going to be some of it. About a question someone asked, did we build any ASR system that shows some state-of-the-art performance? Well, if we build a regular CTC system, it's going to be like numerically identical to building a CTC system with Pytorch because it's the same algorithm. The advantage of K2 is the flexibility. We do have some pretty good kind of okay results in Icefall. We're not better than ESPnet yet because we haven't implemented all of the features like especially the attention model. It's all doable, but we're working on it.
All right. There's one more question from the audience here. Go ahead.
I'm wondering, because right now we relay a lot into the scalability of the CPUs.
Mm-hmm.
I think like everything that has been said is mostly based on GPUs.
Right.
So I'm wondering how efficient it is on CPU and if we can relay on horizontally scale.
Right. So this is a Dan and Piotr question, I think. So the question is, people have spent a lot of effort scaling up things on CPUs, like maybe Kaldi based things. And the question is, since a lot of K2 is built around GPUs, will it also scale on CPUs? Or what considerations will go into it? Dan, you appear to be frozen, but yeah.
Optimized for CPU.
Sorry, Dan, say it again.
They are still pretty fast. But most of the optimization effort has been done with GPU. So like the data structures may not be totally optimal for CPU. Yeah.
Okay.
But most of the bottlenecks have been on GPU anyway. Like for server-based production, I think people generally prefer to use GPUs because it's more cost-effective. For on-device, we might have to come up with optimized versions of some of these algorithms, the bottleneck algorithms, that are more like better, faster on CPU.
Yeah, Dan, we couldn't hear you very well. The audio was a bit garbled. If you don't mind,
sorry,
repeat that. Yeah,
I'll try to repeat.
Yeah.
Basically, it's more optimized for GPU. If in future it becomes a problem, we can optimize some of the algorithms, especially for CPU, meaning like create different versions that are more optimal for CPU. But right now we're worrying mostly about the GPU case.
Okay, all right. So yeah, this time we could hear you better, Dan. Thanks.
Cool.
Okay, so are we all good with questions on the K2 part? So let's do this. We had planned on a 20-minute break, but we ran a little bit over with Q&A. So let's make it a 10-minute break. Again, quick stretch, bathroom, whatever, like, things you want to do. And we'll start back on time at 12:40. 12:40 in Brno, so 10 minutes, please. Thank you. So Dan, you can take a break and Piotr will take over after that. we are back. Welcome back. Hopefully you had some, your caffeine level in your blood has been restored to a more reasonable level. No, you can, there was this, novel I'll recommend to you sometime. He talks about alcohol, but he says something like, my caffeine level is dangerously low. So anyway, we're back. So we continue with the second part. I'm happy to introduce my colleague, Piotr Żelasko. Piotr, take it away.
Okay. Thank you, Sanjeev. So let's move forward onto the next part. There are two parts about Lhotse. The first part, which is going to be right now, I'm going to tell you what are the main concepts, and then we will talk about how you can leverage Lhotse to prepare your data for deep learning. Okay, so the overview. We will start with some motivation. Why do we want to do this? We will do a quick recap of how Kaldi approached this problem and show some differences. And then we will move on to the main concepts of Lhotse. So the motivation, let's get everybody on the same page first. I have this new idea. I want to try it out on a few speech data sets. I want to use my favorite deep learning framework. That will be probably Pytorch for now. And I want to do it easily, quickly. I don't want this to be very effortful in terms of data preparation. That's not my main interest, right? So let's see what corpora are available out there. So for example, we have LibriSpeech, which is the canonical corpus these days. It has 1,000 hours. It's a clean, isolated utterances, red speech. It's very nice to work with, and we're getting very good order rates on it in general. So how does it look like? There's a collection of FLAC files. It's isolated utterance. There's no need to segment anything. And there is a corresponding TXT file with the transcript. Well, perfect. It will be super easy to write a data loader for that. So let's try my idea on something else. So now I have another data set, which is called GigaSpeech, which has 10,000 hours. And they're a bit different. They're still single channel, but these are long recordings now, like YouTube podcasts. They can take 30 minutes, 1 hour. And so, oh, damn, now this is not a FLAC, it's an opus file. I have to handle it somehow differently and probably read some chunks of that. And, oh wait, the metadata is in JSON, so whatever I wrote before, now I have to handle this 2 GB JSON file and do it effectively, efficiently, on the fly maybe. Well, okay, I handled that somehow. Now I have another data set, which is AMI, which is multi-channel and multi-party meetings or conversations. So now each channel has a separate WAV file, and the metadata is in XML files for each different speaker. So, I just showed you 3 corpora, but you are working in this field. You know there is more where that came from, and each corpus is going to have its own idiosyncrasies. And I just wanted to code up my new idea, just, train some models. I don't want to deal with all of that. But hey, what if I wanted to pull all these data sets together and work on them? Well, that quickly becomes unbearable. So let's talk about some solutions now. And this is where we go back to Kaldi. So Kaldi actually has a very elegant way of dealing with all of this, and it's a pretty nice solution. And I can say that because I wasn't the original creator of Kaldi. So how did Kaldi do it? Kaldi introduced this concept of a data directory where each piece of metadata is held in a separate file. We have a file that's called wave.scp, which is the list of the recordings, a segments file, which defines which parts of the recordings are speech, and a corresponding text file, which shows what's the transcript, utterance to speaker file, which tells you which speaker is speaking in which segments, and so on. There's a lot of these. What are the advantages of this? So first of all, Kaldi data directories are stable, and they're adopted by multiple projects like ESPNet or Espresso. They're very convenient for sequential reads and streaming with Unix pipes. Kaldi has a lot of machinery to make this efficient. And Kaldi also provides a lot of transforms on these. So we can do some data augmentation, some manipulation like splitting, subsetting, and so on. And what does Lhotse contribute to that? So Lhotse gives you the first-class Python integration of all these things. So in Kaldi, you would have worked in Bash or command line. Here, you can do this seamlessly in Python. Because of that, it also makes it a bit easier to represent some less common scenarios, like contextual speech. Say somebody's saying something and there is another utterance and another, and we want to model all of that as an example in training or inference. Or multi-channel recordings. It will also be easier in Lhotse. There's no need for a super lengthy step like prepare EGS. If you used Kaldi, you know what I'm talking about. It can take hours or days in some cases to prepare your data for neural network training. And finally, Lhotse is designed to play very well with modern deep learning frameworks like Pytorch. Before we leave Kaldi, a few notes. Lhotse doesn't use Kaldi. It doesn't require it to be installed, but it supports some level of interoperability. We can import a Kaldi data directory with some limitations and export Lhotse manifests into Kaldi. And we also provide implementations of Kaldi feature extractors that are in Python/Pytorch. Okay, so we're moving on to the core concepts of Lhotse. Let's start with a bird's-eye overview. So Lhotse has 4 types of manifests. The first type is called a recording, which just describes the audio file and basic metadata like duration and so on. Then we have a concept of supervision. Supervision is very vague on purpose. It might be many things. It could be the transcript, the speaker, the age, whatever is the task you're trying to solve. The required information would be present in the supervision. We have features, which is pretty self-explanatory, and we have cut. And I'm going to talk about cut later. This is something new that was not in Kaldi, but we're introducing it in Lhotse. The remaining 3 types of manifests have direct relationship to some of the Kaldi files and the Kaldi data directory. So just to give you a concept, and if you have to remember one thing from this slide, it's that the key contribution of Lhotse is you can, the same thing that is in your manifests, you can work with these things in Python. They are named in the same way, accessed in the same way. There is a concept in the databases that is called object relational mapping, which is basically, instead of writing SQL queries for your database, you just have some nice library in your favorite programming language, and it's very easy to use if you know that language. So this is what we're trying to do with speech data in Lhotse. For the manifests, we use the JSON format or a single JSON per line format to store all the metadata. And Lhotse allows you to abstract from where your data is actually stored. So the manifests will contain the information if it's on disk, if it's in the cloud, if you need to run some series of shell commands. And this is all sort of hidden away behind Lhotse interface. So when you call something like load audio, a method called load audio, you don't actually need to think where your data is located. In terms of efficiency, you can just load the whole manifest into memory for small and medium data sizes, and then you can enjoy random access. If there is a very large data, then the metadata is also very large, and you might iterate it lazily. And we also support that. So let's start with the first type of manifest. It's called recording. Recording has some few basic properties like an ID, the sampling rate, the number of samples, the duration, and there is a field that is called sources. When I told you about abstracting away from where your data is located, this is exactly what happens in the audio source class. It can be a file, a command, a URL, and so on. The important thing about recording, it can be a very short or a very long file, and other things that we will talk about in Lhotse later allow you to use particular chunks of that recording. Whenever it's possible, we support efficient chunk reads. If it's a file on your file system, we will try to read just the data that you need, not everything. So when I talked about this correspondence between the manifest and Python objects, this is what you can see here. On the left-hand side, this is the definition, like if you wanted to create a recording in Python. On the right-hand side, this is how it's represented in the text file, the manifest that you store somewhere. And you can easily switch between those by calling fromDict or toDict on recording and all the other objects that Lhotse has. So to make manipulation of these things very convenient, recording is held in a recording set, which acts a little bit like Python dictionary. That means you can query it for particular IDs, access it, iterate over that. But it also has some convenient methods, like you can create a recording set by scanning your file system directory with the single method called fromdir, which is right here. Or going bottom, you can store your manifest from memory into disk or read it from a file. And there are also some nice transformations like speed perturbation or resampling. These, of course, happen on the metadata level, so we don't actually run it on your whole 10,000 hours audio collection. It just notes down in the manifest to do the transform once you request to load the audio from disk. A note about implementation. So in Lhotse and K2 and Icefall, we are using some new features of Python. The first one is a new syntax and standard library module called typing, introduced in Python 3.5. It allows you to specify the types for the variables. Python discards all that information during runtime, so if you give it a different type, it's still going to work. But it works nicely with text editors, IDs, Jupyter notebooks, and static checkers. You can more easily check for correctness of your code. It's also a nice documentation. And the second feature is called data classes. It's a new type of decorator for classes in Python, which makes it more terse to define them. You can see this, the top level of this code. These are just the members of an object. And of course, we can have methods as regular. All right. So let's move on to the second type of manifest called Supervision Segment. This is very much like Kaldi segments, except all the pieces of metadata are stored together. So supervision is gonna refer to a specific recording. You can see the recording ID member at a specific time span, which is identified by the start and duration measured in seconds, and a specific channel in case the recording is a multi-channel object. And there are different pieces of metadata like text, speaker, language. There is also a custom field, so you can add whatever type of metadata you want in there. And you will be using this thing later to construct training examples. Let's take a look at these three data sets I talked before to see how you would construct the manifests for them. So for LibriSpeech, it's very straightforward. You have a recording that refers to a particular file. It has the sampling rate and everything. And for each file, there will be only one recording and one supervision. The supervision refers to the same recording ID. It has the text in a given utterance and some other properties. Note that the duration is exactly the same for both. It's going to be a little bit different for GigaSpeech because we have long recordings here. So the recording object has about 40 minutes. It still refers to one file, single channel. And for each recording, we will have multiple supervision segments. They all refer to the same recording ID, but they have a different ID of their own. And you will notice that the start property is going to be larger and larger for each supervision. We can also model overlapping speech this way, when the start will simply be a lower value and overlap with the previous segment. Finally, for AMI, where we have multi-channel recordings, the recording object is a little bit different. It has multiple audio sources. Each of them refers to a different wave file that is single channel. And in the supervision manifest, you will also note that they refer to a specific channel. And that's right. So we know how to represent different corpora. There is this manifest type, third manifest type called features, in case we want to pre-compute some features. Lhotse also supports on-the-fly extraction, as we will see later, but it's sometimes very convenient to pre-compute these things. And the features object, again, has some key piece of metadata, like the number of frames, number of features, frame shift, and so on. It refers to a particular recording, similarly to the supervision. And it has three properties that start with the name storage. Again, we support different type of storages, and I will talk about this on the next slide. We have a custom lossy compression algorithm that is called Lilcom, and it's a Python package. It's created by Dan. It's designed for log domain features like the filter banks, logmel filter banks. The implementation basically regresses the array elements on their neighbors, quantizes the results, and then uses some standard compression. The amount of compression is controllable, but with the default settings, we get about 70% of on-disk size reduction, which is pretty convenient. And we can store the features in HDF5 files, we can store them in separate files in directory tree. We can actually upload them to the clouds like AWS, GCP, or some other providers. So let's move on to the new contribution of Lhotse, which is called cut. Cut is, the name actually comes from, you can think of director cuts, or in the in the 80s and before, when they used tapes to actually record audio for CDs or for vinyls, they would literally cut the tape and get some part of it. So cut is a view of a part of the recording, but it's not necessarily the same as the supervision. It can be longer. In this example here, we see that the cut that we created is going to cover two supervisions, two utterances, with some acoustic background in between them and after the last one. And it's a part of the recording. So the important thing about cut, again, all the operations that we do on it are lazy, which means we store the information in the manifest, what needs to be done, but they're actually, everything is only executed once we load the audio into memory. And you can see some examples of operations here, which I'm going to talk more about later. These are composable. You can run a lot of operations on a cut, and it's all going to work. Some examples involve just loading audio. You can also plot it if you're using Jupyter Notebook. So we're trying to provide some convenience features if you want to actually see your data or listen to your data, you can also play it. And some standard operations involve truncation, where you use just the first or some other n seconds of the recording. You can pad it with some silence at the end, the beginning. You can mix cuts together with some specified SNR and offset. And the green area that you see in the mixing example, that would be actually a supervision, so there would be some speech segment there. And of course, you can extract features from cuts and store them if you wish to do so. How does it look like in Python? This is just a random example from the code base. You can see that cut consists of other types of manifests. So it has its own ID, start, duration, channel. And then we attach features manifest, recording manifests, or a list of supervision segments that might be overlapping, and so on. And this is the very interesting part. So how do we actually make use of it to represent our speech corpora? There is this base method that is called fromManifests, for lack of better name. It accepts any combination of recording set, supervision set, and feature set. It ties them all together by the recording IDs, and it creates a cut that represents the whole recording with all of the supervision in it. So this is sort of a starting point for doing something else. A typical application for ASR would be to just take the supervisions and for each of them create a separate cut as a training example. So this would be the isolated utterances scenario. And there is a method for that that's called trim to supervisions. It's a method on cut set. It has some extra options that might allow you to have some extra real acoustic context on the left and right hand side of the supervision. Another frequent application would be just to traverse the recording in Windows. This could be useful for voice activity detection, where supervision segments would indicate that there is an activity and lack of them would indicate lack of speech activity. And there is a method for that called cut into Windows with some, again, with some parameters. The third application here is if we just want to extract the background noise from a recording and use that background noise, for example, as a domain adaptation means, mix it with some other data set that is out of domain with different acoustic conditions. And for that, we have a method called trim to unsupervised segments, which will return a list of cuts or a cut set which does not have any supervision, which we presume means doesn't have any speech in it. Note that the design of the cut set is inspired a little bit by the library called Pandas. If you ever worked with tabular data, you will recall it. You can compose the operations in a similar way. Similarly, like in Pandas, they're mostly lazy. And this is an example of a pipeline where, let's say you want to test your code on some very long utterances. You want to use at least 15 seconds, take first 1,000 of them, sample 10 of them, indicate with some special IDs that this is what you chose, and then pad them and mix with some noises, and voila, you probably have a mini batch at this point. Some other operations, similarly like with recordings, you can perturb speeds or resample. We also have perturb volume and tempo, and probably other types of transforms will be coming. In addition to adjusting the recording, it's also going to adjust your supervisions. You might need to stretch them or shrink them. It's going to do the right thing for you. Interesting thing, if you are dealing with some sort of task which involves two pairs of utterances like voice conversion or speech-to-speech translation, you might want to have two cut sets, source and target cuts. And then if you construct a mini batch, you might want to sort them in the same order to have them matching at the same positions. So you might use methods like sort by duration, sort like another cut set, which are useful. And a very simple example of how you could, like a naive example of how you'd implement bucketing. You can just sort all the cuts by duration and split it into 30 buckets. As a bonus, I'm not sure if probably most of you are aware you can use auto-completion these days, and it actually plays very well with Lhotse. If you just press tab in Notebook or some editor that you prefer, you can actually explore the code base this way, and sometimes this is much quicker and more convenient than using documentation. But I still encourage you to use documentation. So one last thing is, for this part, Lhotse also provides a command line interface. That's right. We didn't forget about all of you who prefer to use Bash and command line rather than Python. And there is a main entry point. When you pip install Lhotse, it is going to register a command that's called Lhotse in your path. When you call it with --help, you will see the list of all the commands that we support. It's a subset of what's available in Python, but these are the most, I would say, convenient things. And in particular, I want to talk about two modes, which are called Lhotse prepare and Lhotse download. So we actually have a lot of recipes for preparing manifests for standard corpora that we use in speech processing. You can see a list here. This list is actually larger since I created this slide, and it's constantly growing. For whichever corpora allow public and easy downloads with a link, we also provide a Lhotse download command. So this is our effort to unify how you would work with all of these types of data sets. And this is also available in pure Python. There is a corresponding Python API at lhotse.recipes. So I don't know, Sanjeev, do you want to make a summary? You seem to be doing a very good job of it. All right. So from this part, please remember, Lhotse is building upon, like, we learned from Kaldi's experiences, and we're trying to keep the same spirit, but add some extra things to make this a little bit more easier for the working with modern tools. We have a first-class Python integration. The cut structure, it's supposed to make it easier for you to try new ideas, go beyond isolated occurrences, look at the context, and do many other things. We have a lot of standard manifest preparation recipes, and the abstractions in Lhotse are supposed to reflect how we think about speech data in general, recordings, supervisions, cuts. So hopefully this makes it a little bit easier. All right, how are we on time?
We are almost on time. There's a question online from the Sanjeev. He says, what happens when I cut my recording and the supervisions only partially overlap with the cut?
Ah, perfect. That's a very good question. So,
for example, I have a long recording with some supervised segment. If I cut it into same size windows, some supervisions might not fully fit into a single cut.
That's right. So what happens in this case, let's say when you do these trim to supervisions, cut into windows methods, let's say usually has a parameter that's called keep overlapping. So you can decide if you want to keep these supervisions or just discard them. And if you keep them, it's the duration of the supervision is actually going to exceed that of the cut. So your code that's going to prepare this data for deep learning, for example, can check that, and you can adapt to that accordingly. It's basically up to you how you deal with that, but we're going to make it possible for you to have this sort of information.
There's another question also from him. Does Lhotse provide data loaders for Python?
Perfect. Yes, we do, and that's the topic of the second part.
Okay, perfect.
Okay. Yes?
How can you contribute to Lhotse?
Well, we accept pull requests. We are on GitHub. You can also create an issue so we can have a discussion, and I'm trying to be very responsive, so you're welcome to contribute. Yeah.
Is there an explicit way of doing data augmentation?
Repeat the question for the audience.
All right, I'm sorry. The first question was about how we can contribute to Lhotse. So the second question is, sorry, could you repeat it?
Whether there's an explicit way of doing data augmentation.
Okay, all right. So the strategy that we took for the question, again, is there any specific way to do data augmentation? So the strategy we took is that the augmentations that require you to adjust your supervision information are built into cut set and all the other objects in Lhotse, like speed perturbation, where you might need to stretch supervisions. But other techniques, like, for example, spec augment, or maybe adding some noise, etc., these are also available as Pytorch transforms, and we're going to be talking about it. Yes? Okay, so the question is, have we considered extending Lhotse to video? That's a very interesting question, and early at an early stage of the project, I was thinking about it. I figured maybe we could do that in the future, but maybe by extending the recording class somehow. But at the beginning, we just wanted to be more focused and at least make it really good for speech. But it's definitely possible to extend it to video, so I can see that happening. Yes?
Is it possible already to use it with the current Kaldi? Like, can we export from this to the
Yes, yes, we support export and import to Kaldi. There are some restrictions, some types of data you might run into some issues, but if it's important to you, make an issue and we can figure out how to extend the support. Yes?
How difficult is it to, let's say, integrate some new filter that will process the audio signal into, let's say, with some other, like, user notifications? Is there some interface or some way of?
For some parts of Lhotse there is, like you could register your own storage backends and so on. For other types like augmentations, it really depends. I would say it really depends on the particular feature you're interested in. Some of them are easily extensible and we took care of that. Some others you would need to contribute to Lhotse's code. Yeah, where? Okay. Oh, sorry, didn't see you. That's a good question, yeah. So the question is, how stable is the API going to be? Because we have a warning in GitHub that some things might still change. I think it's we mostly converged on the design. Some things could keep changing, but we're going to try to make it as painless for everybody as possible. For example, like 2 or 3 months ago, we did a breaking change, and every repo that I was aware of, I gave everybody a heads up and some instructions how to modify. So we care about the current users. We're trying not to make it too difficult. Okay. Okay, all right, perfect. That's a lot of questions. I like that. So let's move on to the second part, which is speech data handling for deep learning, or in other words, about Pytorch dataset API and Lhotse.dataset module. So in this part, I'm first going to give everybody a quick recap of how Pytorch data loaders work like. And then we're going to talk about how Lhotse integrates with that and adapts all these abstractions I talked about before into this framework. So let's look at what Pytorch does. Pytorch defines 3 types of abstractions for data loading. The first one is called the dataset, which is supposed to own the data. So you might expect that the dataset might have something like a list of paths to each audio file inside and maybe some metadata as well. And there are 2 types of datasets, accessed by index. So you can index it like a list with 0, 1, 2, which is called map dataset. And another type that you cannot index, you can iterate through it, which is called iterable dataset. The second type of abstraction is called the sampler. And in many cases, like if you worked on image recognition and you worked on MNIST, the sampler would be created implicitly by Pytorch. You might not be aware that it is there, but it's there. And sampler provides the list of indices that are used to query the dataset for elements at particular positions. So it's only used with map dataset. And it's constrained to static batch sizes. So if you say 16, you're always going to have a batch size of 16. And there is a data loader. It connects the dataset and sampler together. So then it's going to query the sampler for a list of indices. It's going to distribute them to the dataset objects, collect the single examples, and run something called a collate function on them. So it's going to convert all the example tensors into a single tensor, maybe do some padding, etc. And data loader allows you to do most of this work in the background. So it's going to spawn multiple sub-processes that are going to concurrently prepare all the examples. And data loader will collect all of these and collate. So how does Lhotse use this API? There's a little twist. The datasets in Lhotse usually won't own the data. The dataset actually would only be used to map a cut set mini batch, so a list of metadata, into a particular batch with all the collation, all the I/O, transformation, collation happening inside this single call to dataset. The sampler, instead of providing a list of IDs, is going to sample cuts from your cut set, and it's going to create a mini batches of cuts or cut sets as well. And this design allows us to use dynamic batch sizes that are based on different criteria than the number of examples. It could be, for example, the total summed duration, number of frames, and so on. The data loader is untouched. You can use standard Pytorch data loader with Lhotse. So let's take a deep dive here and understand the whole process on a more granular level. So if we have three modules here. The first one is the sampler, which in Lhotse is called a cut sampler. We have the data loader, inside of which we have the data set. And we have a training loop, which is actually what you're doing with your model, training it and computing losses, backpropagating it, so on. So in the main train, so we have the sampler in the main thread. The sampler is going to own our data. This would be a cut set that might represent Libri speech, the isolated utterances. And it's going to query it, like iterate over it one by one, collecting cuts until they satisfy some criterion, like maximum duration of the batch. Once this is complete, and this is very, very quick, we end up with a cut set that represents our mini batch, but just with the metadata. No actual data is loaded into our program yet. This mini batch goes into the data loader, and data loader decides which of the workers gets that metadata. So let's say this goes into worker number 1. All of these run in parallel in the background, just to remind. And inside the worker, we have the dataset class. It receives the mini batch cut set, and then it performs the collation on metadata level. So what does that mean? It means it could rearrange the cuts in different ways, for example, to minimize the amount of padding and so on, and maybe apply some cut level transfer, like metadata level transformations. And it's still a cut set at the end of that. Then we perform the actual I/O. So we load all of these pieces of recordings or features, and we're going to do some transforms, which could be Pytorch transforms, NN modules, and so on. And finally, we end up with a mini batch of tensors, which is collected by the data loader from this worker, and it goes into our training loop where we just use this data. So let's see some example of how the data set looks like. And this is this highlighted region of this scheme. So let's say we want to build a very simple data set for ASR. So we start by creating a new class, example ASR dataset. We derive from Pytorch dataset, which is a base class. And we have one member called Extractor. This is something called on-the-fly features that takes a specific feature extractor. We will talk more about this later. And in the getItem method, where we actually get our mini batch from the sampler, we're going to use this extractor to do all the I/O, and we have a feature tensor and a feature lengths tensor in case the recordings or cuts were uneven, and we can just return that as inputs, input lengths, and so on. So the next step would be to get the supervisions, which is the text. So here, there is a little twist. We have several cuts in our batch, but each cut could have more than one supervision, right? This could have like 2 or 3 or however many you want speech utterances. So we actually iterate through all the cuts and through all the supervisions in a cut, and we want to remember which supervision corresponds to which cut, which is the sequence index variable here. And we just have a list of texts. We use the Pytorch's default collate function to convert it into some list or tensor. In the real applications, you might have some tokenizer here to use characters, phonemes, subwords, or maybe even FSAs. And one more thing, because there are multiple supervisions, they could have some offset in the cut. Like if we had 2 speech utterances, there might be, for example, 7-second offset within a cut for the second one. And this is the method in the extractor called supervision intervals. It's going to tell you exactly where does it start in the cut, what is the duration, and what is the sequence index. And we can just update the dictionary with that information. So you might want to do some data augmentation here as well. You can just use a Pytorch module like spec augment and run it on your features. And here is a new thing. I told you about metadata level transforms before. There is a transform called cut concatenate, which we'll look into very soon. And you can apply it here as well. And you might also want to sort your cuts by duration. If you use RNN models in Pytorch, they like it. So let's get some intuition about how this mini batch looks like. I told you about the cut concatenate transform. If we don't use it and we don't do anything smart like bucketing, we have this issue that our batch is going to have a lot of padding, which we see on the left-hand side here. There are at least 2 ways to counteract this. The first would be to do bucketing, so we make sure that all the examples have similar durations. But there is actually a new method that we tried, and it seems to work pretty well, which is to concatenate the cuts. It uses a greedy algorithm so that it sorts all the cuts by their duration, and then it starts from the end, from the shortest ones, and tries to find the longest cut that it can attach it to. And so you end up with examples that might have 3 different cuts in a single example in your batch. And of course, your model has to be able to handle this. And this is what K2 does, actually. In Icefall, as you will see later, we actually do handle this, and our models are ready for this. Oh, one more thing. There is a method in Lhotse called plot batch. It currently works just with ASR batches, but it generates images like this. So you can actually do this with your own data and your own application. And it's very useful for debugging. I found like 5 or 6 different bugs in my transforms just by looking at this data. So it's nice reminder that it makes sense to look at your data from time to time. There is another metadata level transform called catmix. It's going to accept another cut set like musan, and it's going to randomly mix these noises into your batch. Another example is extra padding. So you recall that many models these days use some sort of subsampling, like with a factor of 3 or 4, and you can actually create a bit different examples by just shifting them by 1 frame, 2 frames, 3 frames, and this transform is just going to do it for you. So I told you about the on-the-fly features thing. We call this input strategy or batch IO for lack of a better name. And we support 3 in Lhotse. So all of these just take a cut set and convert it to whatever you want. And what you might want is either pre-computed features. So you extracted them before, stored them, you just load them into memory. You might have on-the-fly features where you provide an additional extractor, and it's just going to compute it for you. And audio samples, in case your model works with audio and learns the parameterization itself, you can just use this. So let's move on to Lhotse samplers. And this is the first part of the diagram I have shown you before. We have this class called cut sampler and multiple variants of it. It's created with a cut set. When you iterate over it, it returns you mini batches as cut sets. Again, it's just metadata. It has dynamic batch sizes. It handles distributed training without any extra effort. You just have to remember to set the epoch every time you increment to new epoch, just like with Pytorch's distributed sampler. It can filter cuts on the fly with a .filter method that accepts another method that tells you, given a cut, do you want to keep it or do you want to throw it out? It's sometimes useful if you have if you have a very large data set, don't want to pre-process it before, and like get rid of too short, too long utterances, and so on. And it can also report statistics about discarded data, like what percentage of data was discarded in total, with a method called getReport. The most typical sampler that you would use for many tasks is called single cut sampler. The single means that it takes a single cut set as input, and each example is a single cut. As you can see on the examples here, you specify max duration, just iterate, and the issue we've seen before, it doesn't do anything smart about the durations, so you'll get very ragged mini batches. And to amend that, you can use a bucketing sampler, where it just creates n buckets, and you see much smaller standard deviation in the durations in each batch. It's also called stratified sampling from statistics, but somehow in deep learning we prefer to call it bucketing. Another type of sampler, which is useful for voice conversion, speech-to-speech translation, and other tasks that have source and target utterances, is a cut pairs sampler. It takes a pair of cut sets, and the batches are tuples, like pairs of mini-batch cut sets that are sorted by the same IDs. Basically, the sampler assumes that your source and target cuts are going to have the same ID, so it can identify them. And again, we support bucketing for this as well. Sampling can be composable, and we're actually exploring this direction a bit more recently. So you could have sampler that takes other samplers and does something funny with it. One application could be you want to mix data sets from different domains, like LibriSpeech, very clean, and Chime6, extremely noisy. And make sure that every mini batch has some percentage of LibriSpeech and some percentage of Chime6 in it. So for that, you could use a zip sampler, and it's going to guarantee that. One quick word about why are we doing the dataset thing differently than Pytorch? Why don't we just use map datasets? Well, the Pytorch, how they do it in image community is really not how we want to do it in speech tasks. We don't have the same shapes in every example. We don't want to have necessarily a constant batch size. We might want to do collation actually before, like, in the background, and all the transforms and so on. So there is a list of reasons. I'm not going to go too in depth, but we gave it a lot of thought actually. But if you have some caveats, we're happy to go into discussion later. So one last thing. What about the really large data? What if I have multilingual LibriSpeech, 50,000 hours or something larger? So it's actually very easy with Lhotse. You just have to make sure that you stored it in a JSON-L format where you have a single cut per line. You can also use compression, and it's going to automatically unpack it. And you have to read it with a method called from JSON-L lazy. And this way, you're telling Lhotse, hey, I don't want to pull everything into memory. I want to read it as I need it one by one. So the con of that, you lose the random access, but you don't have almost any memory footprint. And also, if you want to do some things like shuffling and so on, and Python is too slow for that, you can revert to doing it the command line way with pipes, with just gunzip and gzip. But if you don't want to go back into command line, we actually implement a streaming shuffling algorithm. It's approximate shuffling. It's not going to be as random as if you had everything in memory, but it's going to work. And the whole thing, there are no modifications that you need to your training loop or data loading code. It's basically just going to work with multiprocessing, distributed training. We made sure of that. So a quick summary. Lhotse follows basically standard Pytorch patterns. If you see Lhotse data loading code, it's going to look familiar to you if you're a Pytorch user. We have some off-the-shelf cut samplers in Lhotse for a wide variety of speech tasks. We have some examples of custom task-specific datasets, but we actually expect you to write your own dataset if you want to do something fancy. We're not trying to be overly general and create thousands of callbacks and points of modification. You can basically write your datasets in 15 or 50 if it's very complicated lines of code. The collation and transforms are done on the metadata level most frequently, and only then we do the I/O. This is a little bit different thing. And hey, you can do everything on the fly, but you don't have to. If you prefer pre-computed, you can do it. You prefer on the fly, you can do it. We've got you covered. Okay, so final slide, really. I know Lhotse now. What do I do next? You can install it from pip. You can install the cutting-edge version from GitHub, also using pip. We recommend reading the documentation. It's still going to be constantly improved, but there's a lot of things there. We recommend using the auto-completions and auto-suggestions. That works really well with modern editors. There is actually an example of how you can use Lhotse with ESP.NET, and we designed it to make it very easy to use with any framework that you wish to use it with. And most importantly, enjoy using it. It's made to make your lives easier. Thank you. Perfect. Okay. Yep.
Are there any issues with using this in parallel training?
There shouldn't be. I mean, we do it. Oh, sorry. Yeah, right. So the question was, are there any issues with using this in parallel? Like, I assume, like distributed training or multi-GPU training. There shouldn't be. We do it regularly in Icefall, as Dan is going to tell you also. And it just works. Okay, so the question is, if we put different examples in the same mini batch, does it work with speaker normalization? Okay, so I mean, yeah, you would have to add this somehow as some sort of transform, which you could probably do inside the dataset. You have the speaker labels from the cut manifests. And you might have some additional matrix stored in disk in HDF5 somewhere with some parameters for each speaker. You would load it and you would implement it as a standard Pytorch transform, like an NN module, I guess. Anybody else?
There is a question online which says something like, Lhotse is doing great data processing in general. Will you do neural processing like GANs?
Okay, that's a cool idea. Yes, you could. You could do it, absolutely. I mean, you would have, depending on what the GAN is actually doing and how many, examples you need, how many networks you have and all of it, but you could combine multiple samplers together, get cut sets for, source, target, whatever. And yes, you can absolutely use Lhotse for that. Yeah. Yes. Yes. So the question is, for iterable datasets, do we support something like local shuffling? Yes, we do. I looked up how Web Datasets project does it, and I basically borrowed their implementation, which is you gather some items in a buffer, and every time you add an item, you also shuffle one item. And it's very local, but it's still better than nothing, I guess.
Since we are running short on time, we won't have a break, but everybody stretch with me, extend your hands, go left, go right, twist, touch your toes. All right. No, this is just to, we won't have a break, we'll just keep rolling. If you could bring Dan back on, he's going to do the last part. Hey Dan, can you hear us?
Yes, I can.
Okay, You're back on and you have control as well, so go ahead.
Cool. Okay, well, hello. It's a shame I can't see you guys, but I'm just gonna go ahead. Okay, sorry, I'm doing next, but nothing is really happening. Okay, okay. Let me see if previous works, 1 second. For some reason there's a really long latency in this platform. Okay, so overview is basically I'm going to give you a quick, honestly, I can't remember what that slide said. Okay, so I'll just start from this slide. So there isn't as much in Icefall as there is in K2 and Lhotse. Okay, it went back in the end. Let's go forward again.
There's a bit of a lag then. I think whenever you click, it takes a little time for the actual slide change to happen. So be patient.
Okay. Yeah, but it's like 30 seconds lag. Okay. I lost my train of thought now. Sorry. Let's wait for it to change again. Sorry, guys.
Dan, do you want me to drive the slides? The response here might be...
Well, yeah, that might be better if it lets you do that.
Yeah, so
we are
right
already
now...
pressed it, and it's going to happen at some point.
Yeah,
it's just there's no telling when it's going to be.
Yeah.
Okay, okay, cool. So Icefall is the... yeah, there's not as much as in K2 and Lhotse. We only really released the official version of Icefall a couple of weeks ago. Now, we've been working on this thing called Snowfall for a long time, which is like a draft of Icefall, but that's a bit of a mess. So we generally want Icefall to be pretty open. It's like kind of a demo project for K2 and Lhotse. We don't want to create a big closed system with a lot of infrastructure. We're in touch with the speech brain and the SPNet guys, and we, sometimes we use some of their code, or we, talk about how to improve transformers or whatever. Those other toolkits have a lot of framework, right? There's this whole configuration layer, and you can write these YAML files. This Icefall isn't like that. Icefall is just fairly simple Pytorch scripts, and there isn't that much framework. We may eventually add a little bit more, but I want to keep most of the framework in K2 and Lhotse. So right now, our main recipe is a LibreSpeech recipe with transformers, kind of CGC plus transformer. It's the standard best system that people are using these days. Oh, okay, I think it might be working now. So if you kind of check it out, the directory structure is a little bit like this. I think it skipped a slide. 1 second. Okay, yeah. It has a directory structure a bit like this. So it's a Python library, but the library isn't that extensive. This yellow part is the library directory. There's just a few things in it. Most of it is just the example scripts. But we're moving rapidly on this. Like it's changing quite a bit. So this yellow part is the LibreSpeech example. Right now, we just have the ASR example. And each different system has its own subdirectory where the modeling code lives, where the train.py, the decode.py. So it's the structure is just very vanilla PyTorch. There isn't very much framework here. And we don't even have the models in a shared directory yet. They're just in the individual directory, so we can change them as we will. So this is one of the model directories highlighted, the conformer CTC. This is so a conformer is a recently introduced idea, not from us, from someone else at Facebook, I think, that's like a transformer, but with convolutional layers. And it seems to be giving the best results right now. The other toolkits like ESPNet and SpeechBrain are using this too. So that's that recipe highlighted. But before you do the recipe, you have to do the data prep. So there's this script called prepare.sh that does the shared data prep. That this is valid for all of the recipes for for LibreSpeech ASR. So I'll just show you the script. It's really not that complicated. It's just a bash script, and it calls Lhotse to do the data prep. So Piotr mentioned the download command. So look, it's just doing Lhotse download, and then later on it does Lhotse prepare, and then after that it computes the filter bank features. So this isn't the way you have to use Lhotse. You can do this feature computation on the fly, but it's a little bit slower. So we dumped them to disk. We actually dumped 3 versions of the features to disk with different speeds, kind of like playback speeds. And we're going to do noise augmentation too with Musan, but that one is done on the fly by combining by adding together the filter bank energies. It's an approximation, of course, because when you add the signals, the energies don't precisely add, but it's almost the same. So all of those previous commands create these JSON files, similar to what Piotr showed you. This is one of them. This recipe happens to use HDF5 storage, compressed features. Okay, so later on, this prepare.sh prepares a phone-based lang directory. If you've ever used Kaldi, you'll know what a lang directory is. It's kind of a directory that has the phones.txt, words.txt, kind of meta info about the language. This is not a full Kaldi lang directory. It's kind of a subset, and it's not very formalized yet. We also prepare a BPE version of this lang directory, so that right now we're actually getting the better results with our BPE system than from our phone system. So that's what the conformer CTC recipe is using right now. So this BPE, it's a very trivial kind of lang directory where the lexicon is just, each word has one pronunciation and there's no optional silence. So it's actually kind of unnecessary to use the lexicon FST. We could use a much simpler method if we wanted to turn the words into BPE pieces. So next thing is we prepare the language model. This is an n-gram language model, like an ARPA language model. And this is the small one. This is a 3-gram. We're downloading the standard LibreSpeech 3-gram language model from OpenSOI. Then we're turning it into an FST. And we'll later compile our graph from that. We also prepare a larger version of the G.FST. This is a 4-gram. This one is a bit too large to construct the decoding graph, but we'll use it for rescoring. Rescoring is very easy in K2. We also prepare the decoding graph at this stage. Now, in Kaldi, you wouldn't be able to do this because in Kaldi, the decoding graph depends on the decision tree. In this setup, there's no decision tree. I believe people have been getting less and less improvement from decision trees. We actually made some small attempts to use decision trees here, but it seemed to be a little bit worse. Like, it interacts a lot with other system choices, so don't take that as a definitive thing. But it wasn't easy to get improvements over the standard recipe here. So the decoding graph is called Hclg. Perhaps it should be called TLG because we're using a CTC type topology, and people sometimes call that T. There's no C because we don't use context-dependent phones. It's just monophones, or really mono BPE pieces because they're not really phones. So if you run this script and it's working correctly, it's going to look a bit like this. I think there might actually be more output than this if you haven't done it before, but this is at least some of the output. So now let's go into this conformer CTC directory and try to train the system. Actually, we don't go in there. We invoke it from the top, from the higher directory. We call train.py. Now, all of this stuff with Q-divisible devices and like master port and world size, these are fairly standard DDP things. Like most scripts, I think, that use Pytorch's distributed data parallel will have arguments like this. It's an official Pytorch method for parallelizing training. And this method can also work across multiple machines, although I don't think we've yet successfully tested that. If I'm wrong, one of those other guys can correct me. So the training takes about 3 hours and 40 minutes per epoch in wartime when we run with V100 GPUs, 3 of them. Now, each epoch is actually 3 epochs because we dumped the data with triple replication to disk. And we'll train this for about 20 or 30 epochs for best results, sometimes more. So I'm just showing here what train.py looks like. This is a very normal Pytorch type training script. There isn't a lot of framework, and I actually prefer just having a simple script that's a normal Pytorch script. I feel like sometimes these framework things are overdone. So it's just doing 4 epoch, it's going over the epochs. Then it's calling a function train 1 epoch, and inside there's going to be a loop over the data loader. Now of course, there are some K2 invocations here. That data loader is, of course, a Lhotse data loader. Now the next couple of slides, I guess we're kind of recapping how you do CTC training in K2. So we create a CTC graph using this CTC graph call. This is an example, it's not the real code. Then we compute the loss by turning the nnet output into a dense FSA vec, combining it with the graph, and call CTC loss. CTC loss is just a wrapper that's supposed to be compatible with the Torch's CTC loss function. And you can see they both produce the same number. Like I said, if you implement the same algorithm using K2, you'll get the same result as with other frameworks. The advantage really is that it's much more flexible. So let's say Pytorch is CTC, it has to be a linear sequence of symbols, but in K2 it doesn't have to be. And in K2 you can easily change the topology and try different versions. So decoding, it's with a Hclg graph like I mentioned, or maybe TLG we should call it. This is just a toy version of the graph to show like what it looks like. And as I said, we previously wrote this to disk. You'll be familiar with the PT suffix if you've ever used Pytorch. It's just a torch archive. And I believe if you just do torch.load, it actually comes up with the correct type as like the K2 FSA. Fangjun, correct me if I'm wrong about that. Oh, no. You have to do FSA.fromDict to turn it into an FSA. I think I was wrong. So we generate the lattice by intersecting the dense FSA with the CTC graph. Oh, this is decoding, sorry. Generating the dense FSA with the Hclg with the decoding graph. And we get the best path. And then if we looked at the aux labels of that, the output labels, those would be the words. And it's pretty simple to find, get the word error rate from that. So shortest path. This is the first pass decoding, but there's other passes of decoding. So remember I mentioned that there was a 4-gram language model that was too big to create the decoding graph. So that isn't too big to load as a regular FST. we can load it like as a g.fst and then compose that with the lattices. And this, of course, uses quite efficient GPU composition. When I say quite efficient, it's actually slower than the first pass decoding, I think, just because, you know, these algorithms are way faster than on CPU, but there's still room for optimization. I seem to remember we get very fast decoding compared to other frameworks. It's like 10 times faster than things like ESPNet, even after we do transformer decoding. So yeah, we just compose and get the best path. But before we compose, we have to subtract the old language model scores. So right up here at the top, lattice.scores equals lattice.scores minus lattice.lm scores. So LM scores is one of these attributes, one of these named attributes that we added earlier. And it gets automatically added because the decoding graph had the LM scores attributes. So because it has that attribute, it kind of keeps it, and that means we know which part is the LM scores and which part is the acoustic scores, because the scores is going to contain both of those. So this kind of thing, it's much, much easier to do in K2. If you were to do this in something like OpenFST, you would have had to define a special semi-ring, you know, with a pair or a triple of scores, and it gets quite painful. So, okay, so this is how we do transformer decoding, like attention decoder decoding. Basically, we do it with n-best lists. And the way we generate n-best lists, and we do this because it's an efficient algorithm on GPU, we first generate random paths from the lattice. And the random paths are with probability proportional to the posterior of that path. And then we find the unique token sequences from the random paths. And that gives us an n-best list of kind of variable length. And then we're going to feed this into some Pytorch code that does the transformer decoding. And then this is standard Pytorch. Yeah, so this decoder NLL, it's taking in some kind of, it's taking in the token IDs. I forget if they're a list or a tensor at this point, but at some point they get turned into a torch tensor by padding. And then we interpolate three types of scores, the acoustic scores, the n-gram language model scores, and the attention scores. Now, this is somewhat similar to what other toolkits are doing, like ESPNet and SpeechBrain. Those guys are also interpolating scores. In this case, we're using n-gram scores, and those toolkits generally don't do n-gram decoding, mostly because it's not very easy to do in plain Pytorch. Instead, they're using attention language model decoding, which is, we have to implement this. We've started, but we haven't quite got it into Icefall yet. And that gives a big improvement. Anyway, so after we do that, we just get the best scores from each sublist. All of these kinds of irregular sized tasks are very easy to do with K2's ragged array. At least they're easy to do once you understand the library. That's always the caveat, isn't it? So here's some decoding results. Now, we're doing okay. We're not quite as good as ESPNet yet. And the gap is because we haven't implemented the attention language model yet. So ESPNet has 2.1 on this. And you guys might be aware that people have even gone down below 2% by using large scale unsupervised data. But right now we're just comparing training on LibreSpeech itself, supervised. We don't even have the GPUs right now to do large scale unsupervised stuff. Getting more. So our decoding method is not totally optimal for word error rate, at least at present. It's about 0.1 or 0.2% worse than ESPNet's when we do a fair comparison, but it's way, way faster. It's like 10 times faster. So I've got a pitch for why you should use Icefall and not SpeechBrain or ESPNet, and it's based on Lucky Strike cigarettes advertisements. So the advertisements would go, other cigarettes will, you know, they'll rot your lungs and make your teeth go black, but but Lucky Strikes are toasted. You see, it's totally different, right? So Icefall doesn't have any of those bad things. It's toasted. Joking aside, we're keeping in touch with those other toolkits, and the goal really isn't to create some to suck all of the speech community into using Icefall as an overall toolkit for everything. It's more a demo for our ideas with K2 and Lhotse, and we're going to add recipes, and we're trying all kinds of new ideas, which we're trying to. The main goal is to find cool new algorithms that are much easier to do with K2. But we're going to add a lot of recipes in future to Icefall as well. So we're running low on time, so I'm going to just skip past these. All I'm saying is there's some good resources on the on our homepage, GitHub K2 FSA Icefall. Documentation, collab notebooks, blah, blah, blah. And here's a brief summary slide, but I'm going to hand over to Sanjeev because we need to finish before the end of the session.
That way will stay on. Yeah, okay. All right. So that in a nutshell is where we are. You heard in the beginning about how FSAs are created, stored, manipulated in K2 in terms of ragged arrays, and how FSAs have attributes you can use for various things. And when you compose and do other things, you can keep track of each arc in the output FSA and the arcs in the input FSAs that it depends on, so that you can do autograd. Then in Lhotse, we looked at how to prepare speech. You heard about cuts and cut sets and manifests, and how you can do a number of things lazily, meaning you specify them ahead of time, but a lot of the actual operations happen when you load them. You can work with large data sets and so on, and do data augmentation on the fly. And then finally, you saw one recipe, the Libri speech one, which shows you how to take all these pieces that we have and put it together. Going forward, we're going to build more recipes and keep adding to it. And so there are specific examples somebody might have. Oh, how do I deal with multi-channel recordings? Well, just wait till the AMI recipe is ready and it'll handle it for you, the chime recipe and so on. And so this is where we are. So, well, and why use Icefall? It's toasted. This is just Dan being Dan. So it's like, we'll put up with it. So let me wrap up with one more thing. While we were doing all this, since we proposed the tutorial, it was accepted. Within the last few weeks, we found out that our colleague Yenda Trimal, we just got a National Science Foundation grant. It's a 3-year grant to continue to work on K2, Lhotse, Icefall, and make them generally useful to the community. And so this is great, which means there are some, in addition to the resources that Xiaomi is putting into it, Hopkins also has something now. But more importantly, we remembered that a big part of Kaldi's success was the follow-on hackathons that we had 2 or 3, maybe 4 years in a row. In fact, I was telling you earlier, we got together here in Brno for 2 weeks or so, 3 times in the summer. And we put in that request in this proposal as well. So Yenda has proposed that in the 3 summers going forward, 22, 23, and 2024, we bring together about 8 to 10 people in one place to work on some aspects of Lhotse, K2, Icefall. And the goal is to involve all the community, not just these 3 groups. And Piotr was telling me we already have more than a dozen contributors to Lhotse, and K2 has many contributors. So this is a call for participation. Some features are already on our roadmap and we'll put them in, but we will still need help. Other things might be proprietary to some, not proprietary, necessary for some important project that you're doing. For example, somebody approached us saying, hey, we want to work with some people with speech disabilities. There might be some special data augmentation or alignment work needed, whatever it is. Come join us. There'll be a call out very soon about next summer. So come apply for that, be part of the group, participate. And if it's more than the 8, 10 people we can support, we'll go and hit up our industry friends for more money and we'll make it happen. So one way or the other, this is going to be a community effort. Its success depends on all of us, so please participate. So with that, let me stop. And yes, Yenda.
Just a quick comment. Please do not wait for the call with contributions. You can start
Okay, Yanda says, don't wait for the summer to contribute. Start now.
Yeah.
Yes, that is true. This is simply if we need put our heads together and work intensively for a couple of weeks in a group. That's what we do in the summer. But otherwise, please start contributing right away. Everything is open. Like Piotr said, make issues on GitHub or send in PRs, and we'll work with you to make it a success. So let me stop, and we're kind of out of time. Is it okay if we took a few questions, or do we need a hard stop? Okay. All right, so let's do 1 or 2 questions, and then we can call it to a close. Any questions? Okay, Dan and others are answering the online questions, so those are in good shape. Any comments, any parting thoughts? Thomas? Okay, Dan, so this is you said you're not a big fan of frameworks, but how about PyTorch Lightning, you said, or other things like other frameworks which have more fun features in them? Are we going towards it? Are we not going? Are we? Piotr? And Andra has a question after that.
Okay. So you're free to use it. If you want to build your own recipe for your data, your task, our things should work seamlessly with that, but we will probably not adopt it for Icefall for the reasons mentioned before. You know, it's not toasted.
Just a quick question in relation to K2, what's going to happen with Kaldi?
Okay, so the question is in relation to K2, what's going to happen to Kaldi? Sanjeev, want to take that one?
So at least in the near term, we will continue to sort of, maintain Kaldi is a big word, but if there's a bug, we'll fix it. There are people the thing is, a lot of us have built up infrastructure on Kaldi, so we'll keep it going at least for the near term, let's say another year, year and a half. And I think when Dan and I and Yanda talked about it, and Piotr, our thing was that we will enable a smooth transition, meaning it's not like, oh, sorry, at this point on Kaldi is abandoned, either use K2 or go home. So we will create the conditions so that you can transition smoothly from this Kaldi to either this or another framework, and we hope that this will be competitive. So, okay, no definite date as such. As long as possible, we maintain. Yeah. Okay, in that case, if there are no further questions, thank you very much for attending, and please join us. This is a community effort. We'll do this together.